Hi, my name is Murray Tom. I'm the Vice President of Software and Cloud Services at D-Wave. Thanks for taking the time to join me today. I'm really excited to share some of the hard work our teams at D-Wave have been up to and to show you some of the features of our Leap2 launch. The context for this is that 18 months ago, we launched the Leap Cloud Services to give hundreds of thousands of developers their first access to real-time quantum computers so that they could get resources for their quantum application development and submit jobs and get answers back in seconds. Since that time, we've seen that the number of early applications developed on our systems has jumped from 80 to 200. So developers have been taking full advantage of that access. But what we've learned is that access isn't enough. We also need to be able to provide features to help developers with their key challenges as they're building their quantum applications for production. So with that, I'm really excited to highlight some of the features we've got in Leap. Let me begin by talking a little bit about the field of quantum computing. The background is that over the past 20 years, the field has been filled with a lot of heavy research and technology development. About 2 years ago, researchers at NASA and Texas A&M were able to demonstrate on a D-Wave 2000Q a 100 times speed up over a suite of state-of-the-art classical heuristics that they developed. Move forward a little further, last year, we were able to demonstrate speed up on some important applications in physics problems that have been demonstrated and published in the journals of Science and Nature. So now we have a flood of new entrants into the field of quantum computing who are excited to put quantum mechanics into useful work, finding new ways to tackle problems in finance and medicine and industrial optimization. And that's the platform that people will be building off of to take advantage of this rapidly evolving technology, building towards quantum advantage in the future. So let's focus on how we can deliver customer advantage today. There are some important questions that we all have when we come to quantum computing, and not just the science questions, but also trying to work through a complex field and bring things down to some simple basics. What is the value of quantum computing for our businesses and our applications? And how do we know if there's a portion of our business which has challenges and problems in it that could receive a benefit from quantum computing? If we are able to see that applications are getting built in that domain, how do we translate our complex problems into solutions and also get started ourselves as developers? Or if we have teams working with us who need to be able to leverage the technology, how do we get them started? The Leap design and the features in Leap2 are all intended to provide value in answering these questions, providing the resources and the access and tools needed in order to be able to achieve these results in our application development. So we're providing immediate access to D-Wave quantum computers with real-time responses. We can solve large, complex problems with our hybrid solver service. This is a key challenge we heard from our customers and a point of feedback that the size of the problem that could be submitted to our quantum computer was one of the principal challenges in quantum application development. And the new hybrid solver service in Leap2 effectively allows you to solve problems that are 100 times larger than what's ever been able to be done before. We've also incorporated into Leap a fully featured integrated developer environment. And working within that, you can completely build your quantum application. As well, we've added some new powerful tools, a visualizing problem inspector, which will allow you to see the relationships between the problems that you're solving and how they get translated when they're submitted as quantum machine instructions. As well, you'll be able to see those relationships in the context of the results that you're getting back so that you can gain a deeper understanding of quantum computing, how it's contributing to your application, and also how to performance tune your programs. Through the online community, we're hoping that you'll have lots of opportunities to collaborate and participate in forums in order to learn from those in the community, but also contribute your own knowledge so that there's a compounding benefit for everyone who's building quantum applications. Okay, so the Leap Hybrid Solver Service, this is different from the resources we've had in Leap thus far. You can submit problems of up to 10,000 variables fully connected. And the service will return high-quality answers to you by submitting the problems to a hybrid workflow that will be running on quantum and classical compute resources in the cloud using a portfolio of algorithms. You can continue using our Ocean tools and I'll actually demonstrate how easy it is to modify a program to be able to use the hybrid solver service. That reduces the amount of expert knowledge you might need about processor parameters. It should shorten your learning curves and also shorten the times to piloting and deploying your first quantum applications in production. It's also important to note that we've changed the subscription model for Access and Leap. It's no longer about just getting access to quantum computers specifically, but rather access to all the resources in Leap, so that you can use direct access to the quantum processors themselves, access to the hybrid solver services, or combinations of both, depending on what your application needs are. Here's a view of the integrated developer environment. It's going to come with the Ocean tools pre-installed. It's configured in order to access the quantum computers from the cloud. You'll be able to work directly from being accessed in Leap, wherever you have an internet connection. And we've also published a set of searchable examples to help you get started. These examples are available on GitHub, and in Leap, you can search for them by industry type, application type, or by a keyword. And this should allow you to see what are the kind of problems that other people are tackling, how are they preparing those problems for quantum applications, so that you can then modify them and port them over based on the application data that you're working with. Finally, we have the Visualizing Problem Inspector. This is a first of its kind in the field. And you can see from these images that it allows you to see the data structures as they are formed to be suitable for quantum computers. So I'll go into this in more detail when I demo this for you later, but it will allow us to see the problem forms we're working with in our program, the ones that get translated into quantum machine instructions, results back from the quantum computer, including histogram forms, and some warnings, which will give us some information about how to performance tune our programs. So with that, let me change my screen over to my demo. Here we are. So what I'm showing here is a very short, sort of compressed version of a quantum application program. It starts by importing the open source packages needed to solve the problem. Then there's a second phase here. I'll walk through each of the areas, which in a regular quantum application would be larger and more fully completed. But these show you a bit of a framework of a quantum application program here. In this second section, this is where we would be ingesting data about a network that we would be studying or optimizing over, whether it's a communication network, an information network, a financial network, or a physical network. In this case, I want to show you how easy it is to take a problem, submit it to the quantum computer, but also to then scale up to a larger problem and submit it to the hybrid solver service. So I'm generating my data rather than ingesting it from a data set. I'm actually generating this automatically using a function, which I can then pass the size of the problem in as a parameter, so we can switch from small to large problem sizes. Once that network structure is put in here in this graph, then we're basically putting this into a problem form that's suitable for the QPU. This is being constructed by a function we're calling max weighted independent set. So this is a query, a technique you can do when you're working over a graph, which is you can ask a question, what is the maximum number of sites here, of nodes in the graph, which aren't interconnected to one another? That might be a question you'd be asking in the context of looking for drugs in a database that don't interact with one another, or if you were trying to place physical resources at a series of sites so that they didn't interfere, like with radio antennas, you would want the sites, the largest set of sites that you could choose that weren't interfering with one another. Once you have it in that problem form suitable for the QPU, then we can pass it directly to the quantum processor here. So in this step, we are actually telling the D-Wave sampler function that we would like access direct to a QPU, and then we're passing that through to an embedding composite layer. The embedding composite layer is then going to handle the translation from the problem form that we're interested in working with down to the quantum processor itself, and then we'll get the answers back. So if I click the run function here, this will actually execute this program for us. That has just run directly on the quantum computers in Burnaby. And for that 50 variable problem that we submitted, it was able to find 30 nodes that weren't interconnected with one another. So there were 50 variables in that problem and 54 interconnections. Okay, so let's say we've gone through, we've worked with a prototype example, and we've proofed out version of our problem that is the type that we want to build our quantum applications on, and now we've gotten to the point where we want to scale up to application scale. So in this case, we'll actually increase the node count from 50 to 5,000, and then we'll run this program again to get our answers back. Now, in this case, a 5,000 variable problem can have hundreds of thousands or millions of connections to it. So the hybrid solver service, oh, let me break that briefly. Realize I need to stop that program because it's going to try to run on the quantum processor, and what I want to do instead is run on the hybrid solver. There we go. Here we are. Okay, so with that simple change in our program code here, I've basically stopped the connection to the quantum computer, which was the call to the quantum computer directly, and instead substituted it with a call to our Leap hybrid sampler called hybrid v1. So now, when we're working with this large 5,000 variable problem, it doesn't have to embed it directly onto the quantum processor. It's going to pass it to the hybrid solver, which is going to deploy this across our workflow. So let me run this new program. So when it's passing to the hybrid solver, it's receiving a much larger version of a problem, and the hybrid solver is going to estimate how much time it needs to solve a problem of that size. For a 5,000 variable problem, that's typically about 14.5 seconds. So what will happen in the cloud is that this problem will be received, scheduled amongst other user jobs, and deployed out. It will be running on a combination of best-in-class classical algorithms and making calls to the quantum computer to do large neighborhood updates over that problem. There we've got our answer back. Out of this 5,000 variable problem, we found, the algorithm found 156 nodes that weren't interconnected. And just to take a look at the change in scale here, we've gone from 5,000 variables, we've gone up to 5,000 variables with 625,000 connections. As well, I can run this same problem in debug mode. So I'm going to set a breakpoint here and then go up into debug mode and run one more time because I want to take a closer look at the sample set object that comes back. So I'm going to resubmit that problem and obtain a brand new answer back. And this is the power and simplicity. There is a lot of work that the folks at D-Wave have put in to make this work smoothly at these large scales. And I think that developers are going to find this is very useful in terms of tackling problems in production. However, the counterpoint is that when you're doing a demonstration of something you've made the effort to make really easy, it also looks like a relatively small change to the overall program. So the transparency and simplicity, I'm hoping, will be a feature that you'll all find very productive. Okay, so we've hit our breakpoint in our debugging program. So now I can look at the sample set object, which is actually quite large with 625,000 connections, I think. So I'm going to print this using a print function, which is then going to try to compress the data structure. Sample set, oh, tipped that wrong. Sample set. There we are. So out of 5,000 variables, it can't print them all to screen, so it's just compressed them. And here, returning zeros for all the variables that had value 0. And then if you fully examined all 5,000 of the variables, you'd find that 156 of them this time had the value 1. Those are the ones that identified that didn't have connections with one another. You can also take a look at the sample set, taking care not to misspell this time, .info field, and this provides us with information about the runtime of the algorithm. Now in this case, I submitted the program asking it to run for its default time, but it's also possible to set a time you'd like it to run. This is industrial code, so it can't stop on a dime. And if it happens to overrun the time that you requested, it will report the actual runtime for your programs and your accounting and any performance profiling you might be doing. But it will also report the charge time that it will be applying, and the charge time will be the minimum of what was actually run or what you requested. You might notice that these numbers look rather large. That's because the time for the quantum processors in these hybrid algorithm systems are reported in microseconds. So this is 14.5 million microseconds, or 14.5 seconds. The other field that's reported here is the quantum processor access time. So in that 15 seconds of runtime, it submitted enough large neighborhood update queries to the quantum computer to accumulate 81.7 milliseconds of quantum computational time. Terrific. So now I'll stop my debugging program. Let's leave from here and go into Leap and take a look at some of the other features of Leap2. So right away on our dashboard, you'll see that the Getting Started modal has changed. We still have our Interact with our demos, which takes you to the illustrated demos on the quantum processor, as well as a new section to explore that searchable collection of examples that can be loaded in the IDE or on your local programming environment, as well as a reworked resources page, which I'll take you through in one moment. We've also changed the dashboard and the subscription page, which show you that you now have a subscription, and this shows you how much of the subscription you've used. I have 75.6% remaining. And it also gives us information about the utilization of different solvers at their different rates. So the hybrid V1 solver, for instance, I've submitted 20 problems, averaging at about 13.7 seconds per problem. So I have 66 hybrid solver problems remaining on this month until my next subscription renewal. Whereas with the direct access to the D-Wave quantum processor, I've submitted 51 problems, which total 17 milliseconds. So I have 2,614 problems I can continue to submit with that. Further down here, we have some statistics on the quantum processor that we have online. It's got 2,030 qubits, and its operating temperature is 13.5 thousandths of a degree above absolute zero. And further down here at the bottom, we can see the information we have about our solver endpoint and the different hybrid and quantum processor solvers that we have available here. So with that, let me take you to the resources section. This has been reworked to help highlight some more information about Ocean tools and how to program the systems. Some of the feedback we've got from users is a request to help clarify how to get started with their programming. So this highlights that the Ocean tool software is to help connect you from the applications you'd like to build down to the compute resources you'd like to use, whether they be CPUs and GPUs or quantum processors, QPUs. And you can load examples to run with these Ocean tools direct into the Leap IDE, or you can follow through this link for instructions on how to install them locally. Further down here, we've got links to our documentation and the Ocean code examples, as well as our D-Wave GitHub page with access to all of our tools. We've got a new section down here which provides cards detailing the different tools in the D-Wave Ocean SDK and what their purposes are, as well as links to the documentation and how to view them on GitHub if you'd like to dive into some more detail to see information about the tools, as well as links to tools that have been built by other groups, including researchers and engineers at the Recruit Communications Company in Japan, researchers at LANL working on D-Wave, and also QMASM. If I click on this link here, I'll switch from the tools view to the concepts view. In the concepts view, we've provided information about concepts associated with problem formulation or working with the Ocean tools, quantum computing, as well as hardware-specific concepts as well. And you can click on these to get links through to documentation about that information. Here in the resources section is some summary information about our integrated developer environment directly in Leap. And you can open the workspaces from there. We've also got our illustrated demos, which are now in this location, where you can run and learn more about how to work with factoring or constraint satisfaction problems on our quantum computer, as well as the social network analysis demonstration, which talks about other network analysis problems. And down here, we've also got our other online resources and several learning resources, including this is where our Jupyter notebooks are located, if you'd like to go through and run those. Okay, let me go back to the dashboard at the top of the page. And I'm going to click into our workspaces. So here, this is where I have access to workspaces in the integrated developer environment. And you can see this is the hybrid solver demo that I provided earlier. It was actually running in this IDE. So I wasn't running on my local laptop. I was actually running on computers in the cloud with all the tools that I needed. Here, I'm going to go through and take a look at the maximum cut problem. I can also view this from our dashboard by clicking on the Explore Our Example section. This is where we see all the examples summarized, including with tags by industry, by application type, and by technique, in this case by the hybrid solver. If I look for something from aerospace and I look at these examples and I'd like to switch others, I can also clear my search filters here. I'm going to search for good first examples. And I'm going to see that a maximum cut example comes up here, which I recognize from operations research work that I've done in the past and talked about with folks. And this can be loaded directly in the IDE. But because the system has detected I've already opened this example for this demonstration, it gives me the option of creating a fresh workspace or opening the existing workspace. So I'm going to open the existing workspace. So this is loading this environment directly pre-configured and booting it on the README file itself. And the README file, I can also, by pressing F1 and typing in preview, I can actually load a preview of this restructured text so that I can get the full view of this demonstration talking about maximum cut. Maximum cut is a challenge of taking a graph and dividing it into two groups, a light blue group and a dark blue group, so that we have the maximum number of edges between it. It's a little bit associated with finding the largest amount of redundancy from one area of the graph into another. And this is the graph that we're going to be working with. So I'm going to open up the program code here. So again, this program code has the same structure that I discussed earlier, importing packages, setting up the graph. In this case, we're setting up the graph by hand by actually specifying where the edges are located, but this could just as easily be substituted with some data that could be ingested from the internet or from your local repositories for application data. And then this is being constructed to form a maximum cut problem and then passed direct to the quantum processor. So again, we've specified that we want a handle to a solver that has that is a QPU, and it's being passed through an embedding composite. So now I can run this program, this example, directly here by clicking on the Run from Terminal. This is going to run and submit directly to the QPU and return the answers back. I can even use functionality like the D-Wave ping function so that I can check my connection and see some quick response time on a small problem submitted. Now in that case, we saw that we got these answers back for a maximum cut problem, but what if we want to dive into this in more detail, analyzing the results that we're seeing and seeing if we can do some performance tuning. Okay, so in order to do that, I'm going to go into our program and I'm going to import an extra library here, D-Wave.inspector. And then down here in the program, I'm going to set a breakpoint after the problem has been run. Debug, toggle breakpoint, save the program, and we'll run this in debugging mode. Okay, our program is being loaded. Any moment here it should hit the breakpoint. And once again, we can take a look at the response object, which is here in our program, and we can analyze this in our debugging console by looking at the response. Now, the direct print to screen is a little hard to resolve, so we can also pass this to our print response function. And here we see a simpler summary showing the different nodes that were involved in our graph, which side of the maximum cut they were located on, and the quality of the results returned. But what if we want to obtain a more visual representation of this? We can run the dwave.inspector show function on this response. And this is going to pull up our visual problem inspector here on the screen. Now, if you'd like to, if you're experimenting with this yourself, here I've loaded the problem directly. Underneath this icon, you can actually get references to system documentations. You can also start a virtual tour, which shows you the various features of this problem inspector, as well as some shortcut keys. Let me give you a tour myself. This view here is a graph view, which shows you the problem that we were working on. These are the direct variables we were just working with in our program. And if I go to this menu and I turn off the solution, I'm just looking at the problem form. So now the color shading gives us information about the value that it actually took, whether that's a local bias or a coupling connection edge. To show you a connection here to the actual program, we submitted a problem called problem form called Q. So let's pull Q up. So this is the QBO object, which has biases on variable 1, a value -2, and then also biases coupling variables like as in the variable 3, 4 with value 2, that those numeric values are what we're seeing in this graph view, in this window. And the shading has to do with the value that the bias is taking on a particular variable. Here's variable 3. The solutions appear as dots that are inside the ring. So if I show the solutions, I can see that for this solution in the histogram, this variable 1 and this variable 4 took value 0, and variables 3, 2, and 5 took values 1. But if I switch to one of these other programs, I can see actually that the variables took on different values there. Now, this particular solution at a slightly higher energy is actually showing us a different result for the solution that was obtained within. It actually says that the solution was broken. And we can see down here in the chain break warning that it's identifying that. If I click on this, see here that I've shrunk the screen a little bit too small, so let me just give us a little bit more room to view this in detail. If I click on this here, it's highlighting the node which was involved in the chain break. Now, if I want to take another view of this, I can click to View 2, and in View 2, instead of looking at the results histogram on the right, I'm actually looking at the problem from the target QPU graph. So here, this is the actual architecture of the quantum processor with the qubits represented as dots and the couplings represented as line edges. And here, we can see the qubits involved in representing this variable on the quantum processor from our program. So here we can see that, in fact, one of them has taken the value -1, and one of them has taken the value +1, -1, +1. And that fact that they've taken two different values means that they're not representing a consistent value, a feasible value for that variable. And so that's what's highlighting in our warning. Direct in the warning, there's a link, and when we click on this, this takes us into the documentation and shows us more information about this concept called chains when problems are translated from our programs into the quantum processor and minor embedding, that translation step, with links to more information that describes the task, the architecture of the quantum processor, and how to set chains to get higher quality solutions. So once we've been able to read up on that relevant information for how to tune our program and change the results, we can actually go back into our program and realize that up here, I'll zoom back in again. Up here in our program, we've actually set a chain strength at 0.2. That's probably too low. So we'll bump that up to 2.5. Stop our debugger, save the file, and restart the debugger. This will take us back into our program applying the new chain strength and allow us to then re-invoke the debugger, the problem inspector, D-Wave inspector show. When I run this, this is now going to load the new response that we got from the quantum processor. Zoom out and show this in more detail. And now we can see that on this histogram, which is showing energy on the x-axis, so the more negative on the left, the better quality of the solution because we're minimizing this function. And on the y-axis, we're seeing the number of solution occurrences. So we've got more occurrences, and each of these bars represents a different occurrence where the variables are set differently. So here we see the value 1 on these two corners, but when I highlight this next solution, we can see that all the values of the variables have flipped. And again, we've got a different solution than this top one. But we have no warnings, we've got more diversity and better quality results. Now in this small example, we're tuning for performance, but we did have valid solutions before, but these are important lessons to learn before getting up to large application problems because that's where these kinds of smaller details can play a bigger role in terms of the quality of the solutions that we're seeing. So we're hoping that you're going to be really happy to work with the problem inspector. There's lots of exciting ways to look at the problems in a new form and learn about how programming the quantum computer can be visualized. The last thing I'll show you here, I'll stop our debug program, is that we have a right in the integrated developer environment, we've got a navigation panel which takes you into the different locations of Leap, whether you want some more information from the resources page, jump right to the searchable collection of examples or our documentation. We also have our help center and community, as well as our dashboard and links to our Jupyter notebooks. And from here, I'll check the help center, where you can get more information about D-Wave hybrid, the open source function, the open source framework that we have for building your own hybrid workflows, or the hybrid solvers that we have in Leap that you can program direct in the system. Okay, and with that, I'll switch back over. Thank you all for joining, and I hope that you found this informative and useful. I'm really excited to see the quantum applications that you build in the future. And yeah, get started, have fun.